Hi, this is Jennifer from SFCDI. Just wanted to make sure everyone can hear us. I'm joined with Arturs Neiburgs and Fruin. If everyone can hear us or can't hear us, just send us a message on the chat channel, and we will see if we can fix that. Okay, great. Let me go through the intro slides. Just want to let everyone know that this is just a webinar. Okay, so our next event will be on May 15th, Friday at noon, and then we want to let everyone know that all of our future SFCDI events will be via webinar until further notice. We also want to let everyone know that we have a logo competition. Our logo, as you can tell, on the previous slide, still says SFCDUG, and we want to revamp it to say SFCDI, and we'll announce more details next month. We also want to make sure that we talk about Your Desk University. These have AEC seminars online via webinar, and they have a host of events happening in April and May, and you can check them out on yourdeskuniversity.com and see what they have and sign up for their events. You can also check out their YouTube channel as well. We also want to make sure that due to the current conditions, we want to make sure we do a call for 3D printers. So if anyone has any 3D printers, we want to make sure that you know that there are some things out there that people can participate in making masks, whether you're in California or international. We also want to thank the sponsors, Autodesk and Gensler, for today's event, as well as go on to our future presentations, Computational Design Experience for Building Structures with Arturs Neiburgs, and Dynamo First Aid to the Coordination Nightmare with Fruin from Sigma AEC. I'll let Arturs go first.
Hello, can you see my screen?
Yes.
Okay. Okay, I can start, yes. Hello to everyone. It's a pleasure to be here, and I hope you are doing all good. And yes, as Jennifer said, my name is Arturs Neiburgs. I'm from Latvia, and today I will share my experience in computational design for building structures. At the first, small introduction about me, and my background is civil engineering, and for 10 years I've been working in a holding UPB that incorporates 40 companies. And one of them I worked at most was precast concrete factory, MB Group. And some years ago, I founded a company with my partners, and our main business directions are structural design expertise that's needed for certain projects in Latvia, and BIM management, as well as digital solutions. And last year, I joined my university. I finished, and now I'm a guest lecturer and giving lectures about the BIM And yeah, so today's topic. Today I share some experience we are developing for automated frame building. And the idea is pretty simple. The idea is to type some building dimensions in some kind of tool. We'll do some optimizations within its limits and give out some ready 3D model ready for manufacturing. So this is a simple idea, what we would like to achieve and what we are working for. And in the next couple of slides, I will show some concepts, how we are dealing this to develop this idea. And as long as there is no widely available technologies for creating freeform structures like with the 3D printers, they are emerging and developing, but at this point, they are just a new technology, not so widely adopted and real projects. So we are looking at a traditional way of constructing the buildings. So basically, we choose the structural frame for the building. We do some calculations. We choose profiles and types of connections. And as I mentioned, I worked in the company. It's international. We were working on different kind of projects in different countries. And at that time, I noticed that each of these countries have own traditions, how to deal with the structure, how to choose the materials, and so on. And yeah, for example, in Scandinavia, they're more on prefab structures, and Southern Europe, they're more on custom site or brick laying. So there's lots of choices and lots of possibilities to make these buildings. And so our first approach was to reduce the system complexity, so we would be able to parameterize this building. And the next concept we are developing, it's as we call it, the main infrastructure for all the idea. It's a grasshopper definition. And as you can see, there's an example. With this code, we can create columns, roof trusses, vertical braces, roof braces, internal walls, slabs, and everything else, including foundations. And this code being organized by dividing its by its purpose. Like you can see the gray line, it's input data. The orange line is the main code that is generating the building itself. The blue line is code for generating the 3D model in technical structures, and the purple one is for generating the structural schema or this frame for structural calculations. So in such way, we can easily organize, we can easily maintain this code. And it's like reading from left to right, and we can put another functions in between. It's quite easy, and that's the way we have built up this for several trials and found that this is the best way. And as I mentioned, we treat this code as a main infrastructure for our idea, and if it's poorly developed, then there is issues with execution, some unwanted limitations, and currently we are working on to improve this first version, and we got some experience gathered already, and we reach also some limits for softwares, and so it's a great experience, and we are hardly working to improve this code. Yeah, the next topic I would like to mention, the compatibility and sustainability of the code of the idea itself. And as you know, probably there's so many digital tools and solutions nowadays on the market, and it's difficult to choose for one or couple. And you can never guess if the new tool you choose will be still on market for next year or a couple of months. And my belief is that it's that every time we have a problem and we make a decision for one or another tool to solve it, we actually are causing a new problem that should be solved. And we are kind of stuck in a never-ending problem-solution loop. So every new tool or solution is making maybe some other issues, and that must be solved. And of course, the software versions are upgrading, and you must be sure that they are compatible between each other. And that our approach for this project is that we are trying to use in Grasshopper just built-in code blocks, trying to avoid any third-party code blocks, and so in that kind of way we are trying to make it easier to maintain over the time. Of course, this approach has some disadvantages because we are spending lots of time for solutions that are already on the market available, and still we're making from scratch them. And of course, there's some balance must be found for this approach, but still you have to think about how you will maintain this code and all the solutions in a longer time of period. So. The next about the structural designs, we are looking for the best solutions, of course, and at this point we have tested several approaches, and yeah, we have come to conclusion at this point that it's probably should be done within Grasshopper or test with RFM software that we are using in everyday work. This workflow show that this kind of process does not suit our needs. We're looking to workflow where structural frames are generated and calculation engine can proceed them all and give all the best one. With this software and this combination, we can just generate one by one, and every time we are generating new schema, it's been deleted, so some manual tasks should be done. So at this point, we are also looking at a possibility to use some solutions like Rambus 3D or something like that, and that would allow to test much more of these variations of the building and find the best one. And yeah, there's another issue that probably some of you have noticed also, that structural engineers are basically code oriented, and there should be also to build up some kind of trust into the tool they are using. So it's not also too easy to convince them for using a new tool that is not proved already in a real project. So this is another issue we are dealing. So getting structural engineers into these new solutions. The next concept we are dealing with to get this idea done is the optimizations, and they are very closely connected to the structural design itself. And the task is to find the best frame with reasonable load distribution, less material usage. And there's some paradox we can talk about. If we tend to reduce the weight, it means that we use most suitable profile at the specific load for the specific load. And basically in that way, we are increasing the complexity of the building of the system. There will be many different profiles and joints to save the material. The question is, do we save something at the end? And I'm not quite sure at this point, because the producer will have to buy all these different kind of profiles. There probably will be some leftovers in the stock, so the prices will go up. And the same goes for a builder. They will have to deal with more higher variety of structures and solutions. So it will take a lot more time for them to assemble probably. So also it could increase the price. And there's another approach. If you try to group all these profiles, so we'll have less variations, less different profiles, but at the same time we will increase in the material amounts. And yeah, that's the question: where is the most benefit of all these optimizations? Do we lean on this structural designing, or we look on the wider range? And our belief is that the best optimization, the best solution for the building involves to evaluate the production, the building efficiency as well, and maybe some other aspects. And as I said before, that every country has some traditions and some specifics of the market, so this should be taken into consideration when we're doing these optimizations. So there is also some numbers you can see that some experienced engineer, structural engineer, can achieve in Latvia for simple steel frame building. It depends on the wind and snow loads, of course, but it could be something around 20-25 kilos per square meter for entire building, or 50 to 18 for just a steel roof, for example, if you are using concrete columns. But if we yeah, the question is what we could probably save if we are using all these solutions for optimization. So 50%, 30%, I think they're not quite real numbers. We could talk about 10, maybe 15%. And yeah, that's the main question, the main aspect. How do we plan these optimizations? What do we take into consideration? So the choice between the weight, the profile, the complexity of the system, and of course taking into account the local market and profiles and materials available. The next is about 3D model itself. Basically, when we got all these frames ready, we have calculated, we got optimized. We need to make this 3D model, and Grasshopper code allows us to connect to many other softwares to create this 3D model. It could be ArchiCAD, the Revit, Tecl Structures, or Rhino itself. So it's maybe lots of other, of course. But at our company, we decided for Tecl. We've been working for some while with this software, and in our point of view, it's quite suitable for high-level detailing. And so yeah, you can see the examples made in Tecla, but there's no such a big problem to connect to other softwares. The solutions are available, and with a higher usage of IFC file formats, it's even probably possible to do this already in IFC and used in such way. And yeah, that's modeling code, as I showed before, this blue line, it's looked quite big, but actually it's relatively easily to set up compared to the main code, because we've got already all the lines, geometry, profiles, and so on. So we have to just connect to the this modeling software and realize what's already done by the basic code. And yeah, the benefit of this is we can relatively in a short time period can get all the materials and take the decisions for the next stage of the project. And we can easily change everything and see again what are the results. So these were the main concepts. Actually, at the first, we are reducing the complexities of the system to be able to parameterize it. We keep in mind the possibility of increasing the complexity over time, putting some other solutions, materials, and so on. But we are starting with just a simple one, and the structural design should be able to do the calculations for all possible variations based on Grasshopper generated frames. The code itself should be readable, easy to maintain over time. It should be as open for users as possible to adjust it for specific project needs. As long as there's no widely available technologies for creating freeform structures, optimization must include many more factors, such as available profiles, materials, manufacturing and construction technologies, and so on. And at last we need to think about this 3D model, what format for the model is needed, and how do we create it, and where it will be used. So these are the concepts we are working on to be able to get our idea done. And yeah, there is some examples. It takes some time to generate all the geometry. It's pretty complex, but this code helped us to reach the limits of the softwares. And that was one of the tasks we wanted to achieve. But doing such big code in the project, this was a real project, we found issues with the live link. In some stage, it broke down. So every session knew we had to delete all the building and regenerate from the code again. Yeah, no, it's improved by the Tekla, and there's no issue anymore. And you could see in the video in some place there was this blue slabs generated manually. So this basically was another issue we faced. Normally users in Tekla is using components one by one, but using this code we were able to run all of them all at the same time. And actually we found that Tekla was not able to deal with them at the same time, that those components should be executed one by one, so to make sure that they're correctly displayed in the model. And this was also improved. So yeah, this was great experience, and we can move forward, and there is a much more flexibility to the system, and we can achieve more. Of course, there was also some grasshopper improvements we could done with this project, and here is another example for auto connections we have developed. Basically, the code finds elements, which elements in the model are connected. It can divide them by the floors, and yes, in the case we have removed these connection points. We can set up in the code the distance that will take into account. As you can see here, the points are connected, so joint is generated. And if we say that the distance, allowable distance between elements is 300, so it's generated the connection also. So it's a quite a useful solution to automate all the joints between the structural elements. And yeah, it's very good for prefab structures. That's all from my side at the moment. Thank you for your time, and I hope you got some new insights, and my experience was useful. Thank you.
Great, thank you, Arturs. Let's then go to Scene.
Yup, how's everyone doing?
And then we'll take any questions at the end.
Let me switch displays. Show my screen. You guys see the full screen one?
Yes.
Awesome. All right, I'll get started. So thanks everybody. So today we're going to talk about coordination a little bit. I just wanted to throw this out here. I actually saw this on something. Remind me of all this. So who's a more productive employee? The employee that uses out of the box Safari and Explorer, or the employee that uses Chrome or Firefox? So a study was actually done to find that the employees that went out and sought out tools to make their life better were the more productive employees. And I think that resonates a lot with kind of this workflow. I really did not like the coordination efforts I've been thrown into. So a little bit about me. I despise coordination, and I absolutely love Dynamo. So this class was a good pick. Good topic. Why do I hate coordination, by the way? I just think it's a waste of time when you have information inside of Navisworks and you're either, I've seen big plots of paper thrown on my desk where I have to find the element ID, go track down that element ID in Revit. I've also seen the dual monitors with Navisworks on one side and Revit on the other side. So either way, these are huge data drops. So there has to be better ways to do this and organize the data and get through the data. So that's what we started out to do. So the whole thing that we try to do is build BIM superheroes. So to do that in this one, we're going to utilize the data of the clash detection and the data that we can get for the clashes. Of course, we're going to use some interoperability, being able to eliminate some data drops from Navisworks to Revit. And we're going to be able to build all this with algorithms to make stuff happen really quick and fast. So I have a whole bunch of tools. I don't know if we'll get through all of them. This class is kind of built for an hour-long lecture, but so I'll go pretty quick and reach out to me if you have questions on other ones that I don't get to. So we all know the clash kind of coordination where you can go ahead and do a clash inside of Navisworks and then export that out to Revit via Dynamo and Excel. It's a pretty common workflow. So I'm not going to dig into that workflow here. I'll let you guys, a lot of other people have documented it. But just some highlights, some things about that. Of course, we're going from Revit to Navisworks back to Revit. We got the XML report, the Excel file is necessary. And the biggest thing about this workflow is really lining up your coordinate systems correctly. But we're going to avoid that. But some other things. So let's look at first the Navisworks views. So I believe in view templates can be your best asset in a project. So the first thing that we can do is set up all of these Navisworks views if we have appropriate view templates all the way set up with a little bit of Dynamo code. So all we're doing here is we're getting all the views. We're then removing the null values. This is like 3D views that come in as null. We're then getting the ones that are templates. And then we're then looking for the ones that say Navisworks on it. Since it's a 3D view, we'll make a view for each Navisworks view template. And these templates could be different system types or however your office kind of sets it up. Then we can also export all these views once they're created to Navisworks files pretty quickly, thanks to data shapes. We'll be using his work a lot in this workflow. But yeah, relatively easy. Get your Navisworks views, give it a file path, and get the current document, and then make a file name from the document and actually add the current date to it, so you always know which one's the newest export. So I thought it'd be fun to kind of look at another way of doing clashes, and this is actually doing clash detection inside of Revit with Dynamo. Oh, well, sorry, this one's actually the workflow for going from Excel. You can see we have Excel data coming in. We're then organizing Excel data. On the top, you can see that we're pulling coordinates from our project. We're then translating the coordinate system, and then we're able to place our clashes and set the parameters. But here I want to look at a workflow where we could do this all straight out of Dynamo. So this is really awesome. If you don't have a huge model, but it works actually on the active view, so you can limit it down. So let's say you just modeled an area and you want to know if there's clashes, you could run this really quick, a lot faster than having to go all the way into Navisworks, set up your views, do the Navis export out. So it's a much faster way. What we're doing here is we're actually grabbing the Revit elements. So the elements are our clash family. And then also the, I forgot what we did there. Oops. Oh yeah, we grab all the systems from the active view. So with the systems, then we're able to have that UI pop up so we can select certain systems. I found that's a really good way to be able to get just the Revit elements that you're looking for. We then use a node out of MEP Pover's package, and he has ones where you can get all the elements from a system. We then need to filter these elements a little bit, but then the real magic of the script is a node inside Binorfs, which lets you do clash detection really, really fast compared to doing intersections in the native Revit way. Now, what's really interesting about this, I think, is how much data you can start collecting once you've done the clashes. So I really wanted to see about how much data I could collect just from the information I had, and then what I could do with that information. So here's just some examples. So of course we can get the element of the clashes, the two elements. We can get the system types of the two elements of the clashes. But we can also, from the points, start to hone in on stuff like the level that this clash belongs to, the scope box that this clash belongs to. And then we can even think a little bit more outside the box about maybe the volume. So that way we can kind of look at how big the intersection is of the clash and start to limit down which ones are bigger issues or which ones are just barely nicking maybe because of some insulation and it's not a big deal. Then also, how can we start grouping and ranking all these clashes is a really interesting thing. So clash grouping, so this is our model. If we strip it all away, you can see that. But then like, how can we start to group these clashes to be able to organize and go through it in a thoughtful kind of manner? So there's a couple different ways to do it. One of them is a fun thing that I've used quite often since learning it, and that is k-means clustering. This is just a fun example of k-means where we're using a VAV box to cluster these groups of air terminals. You can kind of see how the VAV boxes move through it multiple iterations to find these clusters. So you can think about using k-means to find massive groups of clashes inside your project. Another method we've used is just grouping stuff by distance. So there's a nice little Python node in there where we can look at the distance between the clash indicators or spheres or whatever object you use. And then you can put a margin on there. So if it's less than 5, in this case, you can see that all 3 of those blocks are grouped together. If it's greater than 5, you can see that they're not grouped together. But this could be ran on all the clashes, and you could start to very quickly group clashes that even overlap each other to start to get a better understanding of where there's a lot of clashes and how to attack the problem. So this is something that we've built then. You could run all this out of Dynamo Player to even kind of set different groupings. So here we have the option of setting groupings by scope box, setting groupings by using k-means, and even setting groupings using the group and the grids I put on there as well. So now we have all this data, right? I thought it'd be really interesting to get it all into Excel and see what we could do. So maybe you could have graphs of clashes solved versus new clashes created over time to see if you're actually causing more problems than you're solving. I've also thought about it'd be really cool to start maybe gamifying clash detection to where every time a clash is resolved, the Dynamo script is able to collect the person's name that solved that clash, and you can start to see how many clashes people are solving and somehow give a little reward system and get the whole team involved and make a competition. But also just being able to analyze the data with graphs and everything, I think is really useful. So we're able to get all the clash data in Excel relatively easy. So we simply have a UI pop up that says, hey, give me select a file path, please. And then we collect all the clash data within the project, and you can see we can write all those parameters that we've already set to Excel. So now we have this huge database to build these dashboards with in Excel or Power BI or whatever it might be. The clash isolator. I didn't finish the video, but this one should be kind of straightforward. The whole idea here is that we have our clashes. We've now grouped them and ranked them with the data that we have. So now we want to start solving them. So what we can do is we can go ahead and get the first clash in all of our clashes, and we can sort all of the clashes by their ranking. And then we can make a 3D view to isolate that clash. And then we can even isolate the elements that aren't involved in the clash or even halftone them. So this gives a really fast way to jump directly to where clashes are and be able to resolve clashes really quickly. The next tool, so let's say you want a clash, so it's really difficult to model in 3D. So this is a tool that you could build to start to reroute clashes with Dynamo. So you would go ahead, select the clashing elements and select the elements that you want to reroute. Have a whole bunch of parameters there for flexibility. Do you want to go to the right, left? Do you want to go up and down? And actually how this tool is working is thanks to Topologic and their tools. So it's kind of built from this idea that they put out of where you have objects impeding this line that it can automatically start to reroute around it. So what you can do is you can start to isolate the view to only get the elements in that view. So now you don't have tons of elements, so you have to check. And then you could go ahead and run this tool to find the best path around it and reroute the tool. So that's how it's working under the hood, is with the Topologic cool Dynamo package. So I really recommend you download that. It's a really good package even for graph theory. I've been using a lot of fun stuff like that. Shortest path, a whole bunch of stuff. So this is the reroute tool. We have a UI pop-up that shows you all the options. Then we have to build the grid around the clash object. This is actually kind of complicated because again, you have to deal with the coordinate system. So you want to make kind of a bounding box, but that's aligned with the element that you're trying to reroute. From there, we can take that bounding box and actually build a lattice inside that bounding box and turn that lattice into a Dynamo graph, or not a Dynamo graph, pardon me, a topological graph. And then from the topological graph, we can run the shortest path. We then can collect all the system data and duct data from the old route, and then we'll delete that old route elements, whether it's ducts or pipes. And then with all the information, we can take that all back together, and thanks again to MEP Pover package, we can build the new route around the element and connect it all back up. The next idea is to really start to document wall penetration. So let's say you're going through your model, the next clash comes up on a wall penetration. So maybe I have Dynamo player, you could click wall penetration. Therefore, we would do the wall penetration, and then we could also even start to document the wall penetration by building the section views at those particular walls. We've also actually done stuff where we've added options. So I'm looking for CMU walls, or I'm looking for concrete walls. So then you could set that into your clash. And then when those clashes pop up during clash detection, you would just run the Dynamo script for wall penetrations and wall documentation. So then let's say we've done all of our routing, we're good on clashes. There's more work to be done then on things like hangers to kind of get to this design build high level of modeling. So this workflow works by finding pipes. It really starts off with the Revit family. So here we have a Revit family. I put the center, I've seen it done different ways, but here I put the center around the loop itself. And then of course the loop is parametric, so it can change. And then that height on the strap changes. So what we're able to do then is we can collect all the Revit stuff. So in this case, we're collecting all the pipes. We then want to filter out those undesired pipes. So this might be, well, it's definitely vertical pipes. So we can look at a parameter to get those and then remove them. And maybe you want to even get angled pipes too. So you could actually get the line geometry of the pipes and look if the Z vector is 0. If it's not 0, then we'll remove them. Right, so then from there we get the element geometry. So then we have the start and endpoints of the element geometry, which is just a line for a pipe. And then we're able to get points cut in a little bit, whichever designated offset you want to go in. And that can be in the user AI. Then we can get the points along that line at a certain distance. Get those parameters. So now we have points along the line. Then we can use the vector information from the line, the direction of the pipeline, to figure out the rotation, a little cross product of the Z vector and the line itself will give you the Y vector. You can use that to interpolate the actual rotation for the hanger itself. And then probably my favorite part of it, my favorite node in Dynamo, is the ray bounce node. So at the endpoint, once the hangers are placed, we'll use the ray bounce node to shoot up and look for categories of either floors, ceilings, maybe some structural stuff, but see what it hits. And from there, we can get the offset height. And then we can set that strap height parameter. We could also do stuff with modeling really detailed level of stuff. So here we're actually just selecting Unistrut to be able to place all those Unistrut straps. So this was, and then also the connectors to the panels and the Unistrut. In this project, we're actually modeling down to the bolts, washers, and straps to be able to do auto documentation and BIM of materials from those individual elements without doing assemblies, since assemblies tend to blow up a model really high. But rather than doing this, we took the human plus computer approach to where the human could go in, select this to place those a lot faster than trying to model to this level of detail by hand. I mean, that would be an absolute nightmare. So the next step then for the fabrication process is this idea to make all the views. So here we're able to select one element just to kind of show how this would work. And so what I like to do is define a 3D view, and then I can make the camera be really whatever I want it with really simple controls. So here we have them all on sliders. So here we brought in a duck and we have everything on a slider. But you can see that phi is that rotation, I guess, in the over the top axis, and theta is the rotation in the XY plane. But we could also feed in then just different degrees. So 90 degrees, well, 0 degrees to get the front, 90 degrees to get the side, 180 degree to get the back, 270 to get the other side, obviously like that for the top. And then you can even get your ISO view by combination of phi and theta. You're then able to send that stuff to, and I didn't have it already documented, but you're then able to send that stuff to a 3D view. And when you lock up the 3D view, right, you're able to start doing dimensioning. So you can have actually Dynamo do the dimensioning on the top view to get like the length. Use the front view and do the dimensioning for the size of the duct, or even just tag the ISO view to get information about the duct, and then put all that on a sheet for your shop drawings. Another aspect about this whole workflow is the fact that if you have a whole bunch of ducts and you do something like this where you cut the ducts at a standard length, we're then able to make one sheet for each duct that's the same size and the same length by just getting that first one. And then we're able to use the element IDs and stuff to be able to organize this stuff together. But you can also see that we can go ahead and dimension stuff on an actual plan view to help get out the door and be documented well. That's all I have. So any questions, I guess?
Thank you. Thank you, Steen. Let me see if we have any questions in our panel. Let's see, we don't have any questions for you guys on here. So I think let's give it a few minutes and see if anyone asks anything. Okay, well, I don't see any questions in for you guys, but I want to thank you guys both for spending your Friday with us and our SFCDI group.
Yeah, thank you.
Thank you.
Okay, great. And I think that's the end of the today's presentation. Thanks, guys.